We are back, Calculus 1 at NC State. We have just had our third test. I just explained why they're not graded today. Hopefully they'll be graded tomorrow. We shift gears very radically at this point in this textbook. Seems a little odd to kind of do it in the latter portions of a chapter, but the kind of getting your thought process going toward taking everything that we've learned to this point in the course and basically throwing it in reverse. So you might think, well, gosh, why did I learn all those derivatives? Well, you'll see how handy they will be when you are taking antiderivatives. So to this point in time in this course, and this is Chapter 4, Section 9, and then basically Chapter 5, and will take us through the end of this course. We won't finish with Chapter 5, but we'll get up to 5.7 or 5.8 is where we'll get in this course. The rest of this course is antiderivatives. Now, they do have other names. If you've heard the name integral, there's really basically two parts of this type of calculus. Differential calculus, that is finding and using derivatives. That's what we've been doing. Now we're switching the directions. We're going to start with the derivative and find the function for which it is the derivative. So that's an antiderivative. Sometimes referred to also as an integral, or this part of calculus would be integral calculus. So we know the derivative. So here's what we've done up to this point. We've started with a function, and then it was our job to find its derivative. So we're going to reverse that. So if we were to reverse that, we're going to start with the derivative, and we're going to find the function for which it is the derivative, the antiderivative. So basically, when you're searching for these things, you ask yourself the question, what has this for its derivative? Now, it won't always look like a derivative. It'll just look like a function. So for notation's sake, the authors in this textbook have called it this. We might as well get used to their notation. If we're anti-differentiating f of x, then they call the antiderivative some capital f of x. So if you see a capital f of x, you could take the derivative of that capital f of x, and you would be back to the function that was basically handed to us to start the problem. So if you take the derivative of capital F of x, you get this lowercase f of x that we were given to start the problem. So capital F of x is just these authors, their notation for an antiderivative. So if you know your derivative rules well, then this will, I think, seem very easy to you, because all you're doing is, well, I know how to differentiate a natural log. What do I get? It's 1 over x. What is the antiderivative of 1 over x? Natural log. So it's exactly the reverse thought process. Now, there are some inherent problems in this. You can probably think of them. Let's say that we started with a function 2x squared plus 5x minus 11, and prior to this section we were finding derivatives and using derivatives. So if that is our function, what is the derivative? 4x plus 5. Now, let's throw that situation in reverse, and you can see what one of the inherent problems is. Let's suppose that we're starting with 4x plus 5, and we want the antiderivative. What has 4x plus 5 for its derivative? Well, you can take it in pieces. What has 4x for its derivative? 2x squared. So we ought to be kind of rebuilding this same function, right? What has 5 for its derivative? 5x. Okay, here's the problem, right? When we took the derivative of this constant, what showed up here?
0.
0. So what's the antiderivative of something that basically is 0? What has 0 for its derivative?
Any constant.
Any constant, right? We don't necessarily know that it's minus 11 or plus 17 or plus 2/3. We don't know what it is. So we allow for some arbitrary constant. In reality, the constant might be 0. That's okay. But it might also be something else, so we have to put in a kind of a placeholder. There is the possibility of some constant, and unless we're given more information, we don't have any idea what that constant is. Now, you have a built-in check on every antiderivative problem that you do, and you should be able to take the derivative of our answer, and you should be back to the original problem that we started with. So the derivative of 2x squared plus 5x plus c, is that, in fact, what we started with? There's our 4x, there's our plus 5. The derivative of any constant shows up as 0, so it does check. What is 2x squared plus 5x plus c? Is that an answer, or is that a whole bunch of answers? That's a whole bunch of answers, because we don't know what c is. So you have a bunch of curves, basically. What about these curves that are 2x squared plus 5x minus 11, 2x squared plus 5x plus 4, 2x squared plus 5x minus 17 over 11? Tell me something about how they appear visually in the plane. Kind of parallel, right? They're not really parallel like lines are parallel, but they're curves that are basically shifted versions, right? Translated up and translated down so many units. So in general, what is 2x squared plus 5x plus a constant? Isn't that a parabola?
Yes.
That opens up. And it's because of the 2, it's a little skinnier than y equals x squared. So we've got a bunch of parabolas that are basically in the same place in the plane. They're just shifted up or down so many units. So if we don't know any more information, then we have, in essence, not a curve, but and it's referred to as a family of curves. They all have the same slope at the same x value. So before we look at what that picture would look like, let's a couple of the more important parts based on definitions and theorems to this point in this section. Function is called an antiderivative or an integral. I know I'm going to call it an integral, so they are almost synonymous, of a function on an interval I if you can basically take the derivative of your answer and you're right back where you started. So capital F of x is the antiderivative of lowercase f of x. Theorem, and the difference between a theorem and a definition, this theorem requires some proof. If capital F is an antiderivative, notice an antiderivative, which means there are a lot of potential antiderivatives of lowercase f on an interval, then the most general antiderivative of lowercase f on this same interval is exactly what we did. We have to allow for the fact that there is some arbitrary constant that is possibly there. So c can be 0 and then it's not appearing, but it's technically still there because there is a constant tacked on. It just was 0.
On every antiderivative, you have to put that plus c, right?
That's right.
Okay.
What are called general antiderivatives. It says the most general antiderivative. So if we don't have any additional information, all we know is the derivative is lowercase f, then we find capital F of x and we put a plus c at the end. Now there are some problems for which later in the text we'll encounter and you'll see that the arbitrary constant will not be necessary, but there's a good reason why it's not necessary. All right, so here's kind of what we're talking about when we have a family of curves. So we found an antiderivative, and our y value, or our capital F of x value, is x cubed over 3 plus c. Now, c could be a lot of different numbers. Plus 3, plus 2, plus 1. Here's our 0. Minus 1, minus 2. These are all antiderivatives of some function. What function?
X squared.
Okay, x squared, right? If we were looking for a function that has x squared for its derivative, well, how did you come up with x squared?
I took the derivative of what's
Okay,
on top.
right? You can always check if these are antiderivatives, and we've got this family of curves. So our capital F of x is x cubed over 3. What if we took the derivative of that? X cubed over 3 is really 1/3 x cubed. And I chose this one specifically because of how we're going to shortcut the antiderivative. This has that nice, clean look to it. What's the derivative of 1/3 x cubed? It's 1/3. What's the derivative of x cubed? 3x squared. What's the derivative of the constant? 0. So the 1/3 and the 3. So all of these curves right here represent antiderivatives of a pretty simple curve, x squared. So they look kind of parallel, but the curves themselves aren't really parallel. What are parallel are the slopes of the tangent lines. The tangent lines themselves have the same slope. So at x equals 0, it looks like the slope is 0 here. It's 0 here. In fact, at x equals 0, isn't the slope 0 on every one of these?
Yes.
Yep. And let's move over here to x equals, I don't know, 1.7. It doesn't matter what you choose. 1.7, the slope is there. The slope is the same, right?
Yes.
And isn't that the fact that's absolutely true, is that regardless of which one we choose, any of these, isn't the derivative the same on every one of them? Right? The derivative is what?
X squared.
X squared on every one of them. So if the derivative is the same, what is the derivative? It's a slope. So the slopes ought to be the same at any individual x value. So whatever x value I pick, it's not a surprise to me that the slopes are all the same. Now, their curves are positioned differently in the plane, but they have the same shape at the same x value. So at this x value right here, the slope is the same on every curve. So the curves themselves aren't parallel, but the derivatives are the same. Therefore, the slopes at any individual x value are the same. So if we know additional information, what do I mean additional information? What
You had a
else?
point or
Okay, if we had a point. If we knew that the answer was x cubed over 3 plus c, and we knew it had to go through this point right here. Well, as soon as you specify a point, then you know which one it is. Then we're not talking about the whole family of curves. We're talking about this one curve that actually contains that point. So as soon as you know more information, typically a point, then you can zero in on one of the family members. Now, sometimes you actually have the curves pictured like this. This may look a little awkward to you on this next diagram. we may start with exactly the reverse. This is a slope field or a direction field. Have you used slope fields before? Okay? Once. Okay? You're not expected to be an expert with slope fields. But the last thing I did on the prior diagram, I came up with a bunch of line segments that were all parallel, right? That's kind of the first thing that's being done here. At a certain point, at the same x value, we would expect whichever curve we choose, we would expect the tangent lines to all have the same slope. Why? Because they all have the same derivative. All we have to do is throw in the same x value. So you can have a whole bunch of curves here, and then as soon as we know what Catherine said, as soon as we know a point, then we know exactly which one we're dealing with. I don't know, can you see a bunch of curves there?
Yeah.
These are kind of like little, this is like a road map, and these are signs, kind of direction fields or slope fields. They tell you where the curve should go based on the slopes at individual points. So I know if it goes through here that the curve is kind of tangent here, and then it would continue up like this. Isn't that what all those slope fields kind of say? That the curve, if it's in that area, it's on its way up. And then what happens in here?
Curves down.
Kind of curves down and starts to do something like this, maybe? But at any individual point, so you kind of have the little signposts that tell you where the curve is going, which is exactly the reverse of what we did before. But which one do you choose? These are all direction fields for this particular equation. You choose the one for which the other information is true. It goes through a specific point. We'll revisit these in when you do differential equations, mostly in Calc 2. Okay? You'll revisit these things called slope fields. But all they do is kind of tell you where the curve should go as it comes through that area. Okay, so our derivative rules that we have accumulated to this point, which that's quite a few, we now throw them all in reverse. If I can find it, we will throw them in reverse. This is by no means is an exhaustive list, but it is a list of things that we know how to take the derivative of. Therefore, we should know how to take the antiderivative of those things. So if we start with a constant times a function, in the derivative process, didn't we bring this little coefficient along for the ride? Doesn't it make sense that we're going the other direction? We should also bring this little coefficient along for the ride. So we basically anti-differentiate little f of x, and these are in your book, so you don't need to necessarily write them down. Then we anti-differentiate that and get capital F of x. What is the derivative of a sum? Isn't it the sum of the derivatives, right? So the antiderivative should work the same way. We should anti-differentiate little f of x and get capital F of x. Add to that the antiderivative of little g of x and get capital G of x. We'll get this one here in a second. What would you expect the antiderivative of 1 over x to be?
ln x.
Natural log. Now that's a little different, isn't it? Absolute value? I don't think we used that. When we were doing derivatives, we took the derivative of natural log of x and we got 1 over x. What's the difference? Well, when we're handed a function, natural log of x, we're to assume that we can only use x values for which they have a natural log. What kind of values are those? Positive, right? Can't take the natural log of 0. You can't take the natural log of a negative number. But when we come up with a solution, we've got to make sure that we can take the natural log of that. The only way to make sure is to take absolute value. So there's a subtle difference. And you'll see that come into play on a problem or two. But when we're anti-differentiating 1 over x, we're creating this function ourselves. We've got to make sure that we can actually evaluate it. Here's a tough one. What's the antiderivative of e to the x? I don't know if I can handle that on a Monday morning. Wasn't e to the x its own derivative?
Yes.
Right? So shouldn't it be its own antiderivative?
Yes.
Makes sense to me. Here's the question you ask yourself. What has cosine of x for its derivative? Sine. There it is, right? So the antiderivative of cosine is sine. Why? Because the derivative of sine is cosine. What has sine for its derivative? Negative cosine, right? If you took the derivative of negative cosine, you'd be right back to sine. What has secant squared for its derivative? Tangent, right? What has secant tangent for its derivative? Secant. So you see it's the same thought process, literally thrown in reverse. We haven't done that one too much. We may actually have to derive that one again. This one is very common. What has this for its derivative? That would be an inverse tangent. If that looks really foreign to you, you might want to jot that one down. That actually comes in handy on quite a few problems. We're anti-differentiating something in this form, 1 over 1 plus x squared. The antiderivative of that is the inverse tangent. Why? Because the derivative of the inverse tangent of x is 1 over 1 plus x squared. Probably haven't used that a lot, but it is one of our, I guess, kind of core derivatives that are kind of patterned, so we can certainly reverse that pattern. All right, let's spend some time on this guy right here. And there's an error in that. I just realized that. Check in your book and see if in that little table that should be an n plus 1. It says n plus 1? Okay. So when we want the antiderivative of x to the n. When we would think of the thought process when you were taking derivatives, didn't you reduce the power by 1, right? Does it make sense when we're going the other direction that we would add 1 to the power? So if we anti-differentiate, we're going to add 1 to the power. Now, if you noticed in that table, it was divided by something. Here's why. We're going to check. We're going to take the derivative of x to the n plus 1. Well, what is the derivative of x to the n plus 1? Don't we take that exponent times x to 1 degree less? What is 1 degree less?
N.
N. So do we want that there? I don't see it right here.
No.
So we're going to, when we check this and take the derivative, we're going to generate an extra factor of n plus 1 that we really don't want there. How can we plan ahead to get rid of that extra factor that we're going to generate?
1 over n plus 1.
Divide by it. So the antiderivative of x to the n is going to be x to the n plus 1 divided by n plus 1. Now let's check that. And by the way, divided by n plus 1 is the same thing as 1 over n plus 1, right? Do we get x to the n? That's what we want. We're trying to find the antiderivative of x to the n. Doesn't this coefficient come along for the ride? What's the derivative of x to the n plus 1? N plus 1, x to 1 degree less. Did we come up with, in our check, what we, in essence, started with on this problem? Yes. Because these two knock each other out, we're left with x to the n. So here's the antiderivative of x to the n. So add 1 to the power, divide by that new power. when will that not work?
When it's negative. Oh, no, it's a negative.
When n is negative 1. Okay? Now, if you didn't know, you haven't had antiderivatives or integral calculus yet, how could you look at this thing and know that it's not going to work at n equals negative 1?
Because x is 0 would be.
Because you'd be dividing by 0. So we'd have x to the 0, that's okay, but divided by 0, that's not okay. So this particular rule is going to work a lot, but it is not going to work when n is negative 1. And I'll contend that we already have a rule for that when n is negative 1, but let's do some example problems with this before we leave this. So on all these down this page, we want the antiderivative. Okay, what's the antiderivative of 3x to the 5th minus 2x squared plus 11x minus 3? We're searching for the function that has this thing for its derivative. So I'll use the author's notation. We have little f of x. We're searching for capital F of x, the antiderivative. According to this rule, we should be able to, and other rules that we looked at on that page, the 3 should come along. What's the antiderivative of x to the 5th?
X to the 6.
Yes. Is that the rule?
Yes.
That's the rule. It's supposed to work all the time except when x is negative 1, and I don't see any of those in this problem. Bring the minus 2 along, just the way we did in the derivative direction. X, the antiderivative of x squared is x to the 3rd over 3. Same rule. Bring the 11 along, x to the
X squared over
x to the
2
2nd, or x squared over 2.
minus 3x. Yeah.
And then don't we also have to have a plus c? Now you might want to rewrite this. You don't absolutely have to, but 3 over 6 is 1/2 x to the 6th minus 2/3 x cubed plus 11/2 x squared minus 3x plus c. And we're just starting with this, so we should be able to check. And you're not going to check every problem, but this is day 1 with antiderivatives. We should be able to take the derivative of this and be right back here. Is that correct?
Can we leave it on simplified so that way it's easier to derive it?
It just depends on what we're going to use it for. So what's the derivative of 1/2 x to the 6th?
3x to the 12.
What is it? 1/2 x to the 6th. Wouldn't we bring the half along? And that just reminded me of part of the problem now is you're going to be thinking antiderivative, and then you're going to be checking it with derivatives. So you're going to have to remind yourselves which direction you're going now, because you're doing both, differentiating and anti-differentiating. So the derivative of x to the 6th would be what? 6 x to the 5th. Bring the 2/3 along. Derivative of x cubed would be
3x squared.
3x squared. Bring 11/2 along. Derivative of x squared.
2x
Derivative of minus 3x.
minus 3.
And derivative of any constant
0.
is 0. Is this the same thing we started with?
Yes.
So you have a built-in check for every antiderivative problem that you do. Not that you have to do that, but now I chose specifically positive integer values as our first example. But the rule doesn't say anything that that they have to be positive integers. It just says that we can't use n equals -1. So let's start with our little f of x, 5x to the -3rd. That's not a positive integer. It's a negative integer. How about 8 square root of x? That's not an integer at all. And how about 13x to the -7/8? That looks delightful. So what's the capital F of x? Okay, so you've already gone through the whole process. Let me take that in stages. The 5 comes along. The same rule that we've used successfully to this point. I don't see an exponent of -1, so it's got to work. What's x to 1 degree larger?
-2.
Right? We add 1 to the exponent. You might want to rewrite that before we do the antiderivative. Isn't this 8x to the
1/2.
1/2? So the 8 is going to come along for the ride. How about the antiderivative of x to the 1/2?
X to 3.
Good. X to the 3/2. We add 1 to this exponent and then divide by that new exponent.
Or can't you just times it by 2?
Yes. The coefficient comes along for the ride. How about x to the -7/8? What should we do with that?
Add 1.
Add 1 to it, which is 1/8
Yes.
over 1/8. Put a little plus c on here, and let's move on to a problem that's actually going to challenge us, right? That's how good we are already. Again, you can rewrite this. Now, when you have negative exponents, you can leave them negative exponents, or you can put them in the denominator, kind of where they belong. It just depends on the problem. So as Catherine said, we're going to take 8, and if we're dividing it by 3/2, it's the same thing as multiplying it by 2/3, which would be what? 16/3? 13 divided by 1/8 is the same thing as 13 times 8, which is what? Or 104? Does that sound right? So there's our solution. Again, you've got a built-in check. I'm not going to take the time to check this right now, but you could take the derivative of capital F of x, and you'll be comparing that with the original lowercase f of x to see if they're the same. Is that all right to move that? Everybody feel comfortable with that? So let's say our little f of x is 5 over x. We want the antiderivative. So this is the same thing as 5 times 1 over x.
Natural.
There we go. 5 comes along for the ride. What has 1 over x? Okay, there it is. There's the one so-called bad value for our shortcut, because isn't that the same thing as
X negative.
x to the -1, right? So we ask ourselves this question. We can't use that same rule. We know that. What is it that we could take the derivative of? I know that's poor English, I'm sorry. The derivative of 1 over x, the derivative of something is 1 over x. What is that?
ln x.
Natural log. Okay, and we can start with that because we know we can take the derivative of natural log of x and get 1 over x, but we're kind of creating our own function here. We've got to make sure we can actually evaluate it. So we can only take the natural log of things if they're positive. So just in case the x's that we're dealing with are negative, we've got to be able to do that. And we're doing a general antiderivative, so we're allowing for any possibility of any constant tacked onto this. So the one case for which the rule does not exist, we've already got a rule. the antiderivative of 1 over x is natural log of absolute value of x. Okay, a couple of word problems. Let me kind of switch the order I was going to do them. I want to make sure we get through this one. We want to find our distance, height, or position function. But we're not going to start with that. Normally, we start with that, take the derivative, and get what? If we started with this, and we took the derivative, what would we have?
Velocity.
Velocity. And if we took the derivative again, we'd have acceleration, right? We've seen that problem several times. Now we're going to start here. How do we get back to velocity? Antiderivative. And once we're sure what the velocity equation is and we want to work our way back to the distance, height, or position, antiderivative again. So let's say that there's a free-falling object, and the acceleration of that free-falling object is only due to gravity. So here's an example. So it has no way to accelerate itself. So it's accelerating or decelerating, technically, only due to gravity. So it's negative 32 feet per second per second. Is everybody comfortable with that number? Yeah, and in meters per second, it would look like another number, but it's the same. It's still acceleration. Negative 9.8, right? Meters per second per second. But we're in feet here in this example. So if we start with acceleration, and it happens to just be a number, by the way, right? Just a constant. And we want the velocity, we're going to have to anti-differentiate. So we ask ourselves the question, and we want a function of t, right? T for time. What is it? What function of t has negative 32 for its derivative? Okay, and I heard a plus c. So we've got to have additional information to find out what the actual velocity function is. Let's say its initial velocity. So here's a piece of additional information. We know that the initial velocity is 64 feet per second. So we throw that into the function. The velocity is 64. Negative 32 times t. Well, if it's initial velocity, t is 0. So with this particular additional information, or this constraint, what is c?
64.
c is 64. So there's our velocity. This is kind of like a point, isn't it? When t is 0, v is 64. So now we know the velocity equation. Now we can anti-differentiate again. We want a distance, height, or position function. So we ask ourselves this question. What has negative 32t for its derivative? Negative 32
T squared.
t squared over 2,
64x.
right, t. What has 64 for its derivative?
64 t.
64t, and then we have another c. I'll just call this something different, c1. So at this point we have, and this ought to look familiar, I hope, negative 16t squared plus 64t plus c1. We again would have to have an additional piece of information to find c1. Let's say its initial position is 100 feet off the ground. It's this object that's projected upward started 100 feet off the ground. Top of a building, top of a platform. So its initial height is, so at time 0, the position is 100. So we can plug that in. 100 negative 16, 0 squared plus 64. This is always the easiest when you're talking about an initial velocity or an initial position, because you're plugging in 0 for t. So C1 is 100. So our distance or height or position is kind of all those. So there's our final answer. We've anti-differentiated twice. We had 2 additional pieces of information, initial velocity and initial position. Those were basically to help us find the c values along the way, right? Now, can you see the different pieces of the function? When you look at this 100, what was the 100 in this problem? That was its initial position, right? Sometimes called S sub 0. Also, since we kind of built this function ourselves, what was the 64 as we built this function? That was the initial velocity. And if this were, let me kind of go back to what this was. If this were negative 32 t squared over 2, what was the negative 32?
Gravity.
That was the gravity factor, right? Acceleration due to gravity. So when you see a function that is in feet and seconds, like this one is, you can look at the different numbers and you can just peel them right off and know exactly what they are. So this function could be written kind of generically as 1/2 g t squared. Is that correct? There's the 1/2 division by 2. There's the g, and there's the t squared, plus the initial velocity times t, plus the initial position. Now, if you've taken a physics course, this is probably old hat to you, right? You've seen that and used that many times. So acceleration due to gravity is, as long as it's in feet and seconds, which it was in this problem, then you could, if you knew the initial velocity, you could plug it in. If you knew the initial position, you could plug it in, and you don't have to anti-differentiate at all, because that works every time. All right, let's suppose we want to answer this question. When does this object, whatever it is, when does it hit the ground? Do we now have the ability to answer that from our final answer?
Yes.
Here's the kind of the end result. There's its distance, height, or position.
Position.
Okay. When would it hit the ground?
0. And that's 0.
We want to know when the distance or height or position
It's
is
0. The whole thing.
0. So now that we have started with acceleration, developed the velocity equation, found the c, went from velocity to distance, height, or position, found the other constant. Now that we have this equation for distance, height, or position, all we have to do is plug in 0 for its height. Isn't that true when something is on the ground? Its height is 0. Probably does not factor. Be nice if it factored, but it doesn't, probably. So couldn't we solve for the variable that's being squared by using quadratic formulas? So that would look like what?
Negative 64 plus or minus b squared.
B squared, 64 squared, minus 4 times A times C,
Over 64 squared.
all over
100.
twice A.
Yeah. Times 100.
So are we going to get two t values? Are we going to get realistic answers for this problem? Better not put that one on tape. Certainly we are, is what Eric said. Okay? How do we know we're going to get realistic answers? Because we've got minus this negative. We're going to be able to analyze this. Let's make a picture of this thing. Where does it start? At time 0, where does it start? 100 feet off the ground, right? And it's projected upward with an initial velocity of 64 feet per second. So it goes up, it reaches its peak, and then it comes back down. This is what we're looking for, right? Doesn't this have two answers? That's two answers.
Has a negative answer.
Okay, it has a negative answer. It's going to give us this answer right here, right? Kind of the other x-intercept of this parabola. That's a ridiculous answer for this problem, right? Because we don't know where this object was a second or 2 seconds or 3 seconds before it was projected upward. So you're going to get two answers, one negative and one positive. Obviously, we're going to reject the negative answer. Doesn't make sense in this problem. It makes sense when you're talking about the function. Yeah, the function has two x-intercepts, but it's a real-world problem. We're not going to be able to back up the clock, not like we did Saturday night or early Sunday morning. That you can't actually do that in a real-world problem. So we would find the positive solution. But we couldn't do that until we had this equation. You can't do it from an acceleration equation. You can't do it from a velocity equation. All right, real quickly. I think we can do this in about a minute. That's about all we have. There are some problems that discuss rectilinear motion. It means that something is moving in a straight line. So it moves this direction for a while, and then it comes back, and it moves in a straight line, and it comes back. There's a problem with this, is that you can't really see when it stopped and changed direction. So a lot of times you'll see a rectilinear motion problem diagrammed like this. Even though the path was not like this, the path was all in the same straight line, you can at least see that it came this direction for a while, and then it turned and went this direction for a while, and then it turned and went this direction for a while. So you might see a diagram like this. Let's say the acceleration is 5t minus 3. The initial velocity is 5 centimeters per second, and the initial position is 7 centimeters. So it starts on the 7 centimeter mark. That's where it starts. So if we know acceleration, what do we do to get velocity? Anti-differentiate. Tell me what to write down for velocity.
5 over 2 t.
5t squared over 2,
Yes.
right? Minus 3t plus a constant. How do we find the constant?
Equal to 5.
Okay, it's going to be 5, right? Because when t is 0, the velocity is 5. So if you plug 0 in here, you get 0 in here. So it means the constant has got to be 5. So at this point, we know the velocity function is that. How do we get the location or the position function that goes along with it? It's not type.
Antiderivative.
Antiderivative. 5 halves comes along for the ride. What's the antiderivative of t squared? T cubed over 3. 3 comes along for the ride. Actually, negative 3. Antiderivative of t. Antiderivative of 5. Possibility of another constant. And we know that the initial position is 7. So we could plug in t equals 0, there, and there. Don't we get 0 each case?
Yes.
Right? So we plug in
0.
C2 and 7,
Yes.
right? C2 is 7. 5/6 t cubed minus 3/2 t squared plus 5t plus 7, right? Now, it's not something that's projected upward and runs out of velocity and gravity takes over. It's something that moves along a straight line, but the procedure is basically the same. Let me ask you to take a brief look prior to class tomorrow at some things and just see if you're familiar with some of these things. And then I'll get an idea from you at the beginning of class tomorrow if these are things that you have seen and used before. These are on page A44. And we'll start to work our way through some of these. Deals with sigma notation, summation notation. I will see you tomorrow. Maple 4 opens today. I knew you'd be thrilled.